Hi everybody, welcome back. In our last series of videos, we were looking at the gold standard for causal estimation, which is random assignment. And in the end of our last video, we talked about some of the problems with random assignment, why it's not always going to work, because it's often costly in terms of time, in terms of resources, potentially unlawful or unethical to find random to assign people into random groups to look at the outcomes of certain policies. And so what we turn to next often is regression. And so in these next few videos, we're going to be talking about regression, what it is, what it's doing, how it's attempting to uncover causal effects, and eliminate selection bias coming from unobservable variables. So let's dive in here. In this first video, we're just going to do a little bit of an introduction, look at a simple regression equation, and start looking at the tools here. So regression, and in particular, we're going to be looking at linear regression, meaning we're just going to be using a linear function. So this is a foundational tool in econometrics. Foundational tool in econometrics. And the idea behind it is this. Regression-based causal inference is predicated on the assumption that when key observable variables have been made equal across treatment and control groups, then selection bias from unobservable variables is mostly eliminated. So that's quite a bit here. Let's go ahead and write that down. Regression-based causal inference is predicated on the assumption that when key observable variables have been made equal across treatment and control groups, then selection bias from unobservable variables is mostly eliminated. Then selection bias from unobservable variables is mostly eliminated. Okay, and remember, that's the key. It's hard to control for unobservable variables. We don't know. We don't know, or we can't measure a lot of things about people or about firms. And so, if we can control for as many observable things to make observable differences equal across groups, then we can have some reasonable level of confidence that unobservable variables may be controlled for as well. Okay, and so how are we going to control for observable differences? Controlling for observable differences. That is going to start out from the basic foundation of a simple regression equation. Okay, and so let's, when we say simple, we just mean one variable. And then we're going to extend that to multivariate or multivariable regression. But a simple regression equation looks just like this. As we've seen in the stats review video, actually. So yi, subscript I, is going to be equal to beta 0 plus beta 1 xi, where I is equal to 1, 2, all the way to n. And I is just a subscript for the number of individuals, or if you're doing a firm level or country level analysis, I is going to be subscript for firms or countries. But let's talk about this in terms of individuals. And so if we're talking about individuals, n is the number of observations, So for example, individuals. I is each observation individually. Okay, so if we had, say, 100 people, n would be 100, and I is equal to 1 is person 1. I2 is person 2, so on and so forth. Okay, so that's just getting some of the basics out of the way. Yi is our dependent variable. Sometimes called the outcome variable. Okay, that could be something like one's health, if we're gonna use the same idea from the random assignment chapter. If we're trying to look at health outcomes, some measurement of health would be an example of a dependent outcome variable. Xi are the independent variables. In this case, there's just one independent variable. Okay, beta 0 and beta 1 are regression parameters or coefficients. This one, as you can see, it's all by itself. It's just going to be a number all by itself. This is the constant regression coefficient, or the intercept. Or the constant regression coefficient. Beta 1, which goes together with xi, that is the regression coefficient on xi. And so, for example, that could be health insurance from our previous example. So what's the effect of health insurance on health? Beta 1. Beta 1 is the effect of health insurance on health. Remember from our previous video that we can think about beta 1 as the change in y over the change in x. So how much does health change whether or not you have health insurance? And that's this idea of beta 1. It's the relationship between x and y. And if well designed, we'll talk about that. But if your experiment or your regression is well designed, then beta 1 is the causal effect of X on Y. So how does health insurance cause changes in the difference in health? Okay, and so if we think about this equation, then yi is equal to beta 0 plus beta 1 xi. And if we wanted to think about this as health of person I is going to be some number on the constant coefficient plus the coefficient on health insurance. So if we look at this of person I, health insurance for person I. So if we look at this, we're kind of asking ourselves, what's the effect of health insurance on health? But the issue is that health insurance is not the only thing that affects people's health. And because of that, we add to the equation what we call stochastic error term. Stochastic, ultimately, it just means random. So the random error term or the stochastic error term. We're going to add this in, and we're going to add this in. Let me give you this is going to be a epsilon I. The reason we add this in is because if we ask ourselves, does all the variation in y come from x? So does all the variation in my health come from whether or not I have health insurance? And the pretty obvious answer to that, most of the time, is going to be no. So what we need to do is we could add more x variables, but there still might be, health is a factor of whether or not I have health insurance, and my number of hours exercised per week, and number of calories I intake. But even if I add more x variables, there's still going to be some randomness in my health. So we could add more x variables. But even then, there will likely be unexplained variation in y. But even then, there will likely be unexplained variation in y. Okay, where could this variation come from? Well, if we think about what we have here, the first thing that's missing are just a whole bunch of other variables that affect health that we could even think about. We call these omitted variables. So we could think about how much do I exercise, what's my diet, what's my family history, so on and so forth. Why else might the variation in our outcome be different than expected? It could just be due to measurement error. So if I ask somebody, what's your health 1 through 10, there's going to be a lot of differences in the way people answer that question, especially as subjective as it is. Or even when things are measured with some more objective measurement, like you're trying to explain people's incomes. People may or may not report their incomes based on base salaries versus salaries plus bonuses, whether you're thinking about earnings, whether you're including taxes, so on and so forth. So there could be a number of sources of measurement error. This one can be corrected a little bit. Omitted variables is something that we're going to be talking more about. That's an important one. Another possible problem could be incorrect functional form. Incorrect functional form. So for example, we might be using a pretty normal linear function, y is equal to beta 1 plus beta 0 plus beta 1x, but maybe we should actually be using something like y is equal to beta 0 plus beta 1 log of x. All those should have i's. And so if we use the wrong functional form, there could be differences there. So all of those are actually, problems that, if designed properly and thought about properly, we can fix. But some things are actually totally random or unpredictable occurrences. Okay, and so ultimately we want to try to fix these first ones, and then ultimately this last stochastic error term hopefully only will capture that after everything is said and done. So to account for unexplained variation, which we can call that unexplained variation the error. In our models, we use a stochastic error term. Stochastic, which again really just means random error term. And that is our epsilon I. Okay, and so when we add this into our model, we started with yi is equal to beta 0 plus beta 1 xi. We can now add to each individual a stochastic error term so that we now have my health is a function of health insurance plus a bunch of randomness. Now, if I don't include omitted variables are in here, and a lot of other things are in there. That's what we actually want to try to get out of there, so that this is only left to what is actually random. And so what this leads to is multivariate regression. And this is where we start adding in variables to try to remove any of the, or to try to include any of the omitted variables. So if we started with yi is equal to beta 0, then we have beta 1 xi, but then we start adding more. So we have beta 2 times xi. Actually, okay, let's do x1i is the first independent variable. x2 is the second independent variable for each person I. plus beta 3 plus beta 4. Let's just use a few instead of doing it totally generic. Beta 3 x3I plus epsilon I. And so what you can see is that now, again, if we're thinking about this as, for example, health of individual I, we could do the first variable x1 that we're most interested in could be our health insurance variable. But then we want to control for every other thing that might be impacting our health. Let's write this out a little bit more. Health insurance. And if that's the effect we want to see, we need to include other variables. So beta 2 might be my age, because my age is also going to affect my health. Beta 3 could be hours exercised, per week or something for individual I. So on and so forth. There could be a lot of other ones that you should include, but ultimately you're going to end up with an equation that looks like this. And really, let's actually, to actually show that we would include some more, let's add those dots in there. And so then in the end, what we have is some equation with all the variables that might affect our health. This one is what we call our primary independent variable of interest. Independent variable of interest. And in a causal type of situation, we can think about this as our treatment. And then all of these other ones here, these are all other independent variables used to help ensure equality across the treatment and control groups. Across the treatment, let's do this, treatment and control groups. And then we have our random error, stochastic error term. Okay, and so these variables, remember in our last video on random assignment when we looked at this, when we looked at people with health insurance and no health insurance and looked at their health, we saw that people who had health insurance, they had higher incomes, more education levels, and so on and so forth. And so what these other control variables, we could kind of think of these as other control variables. That's helping to keep these equal across the treatment and control group so that we are controlling for, we're going to find essentially with this is we're going to find groups of people who have the same age and the same hours exercised, but one has health insurance and one doesn't. And so that's what adding all these control variables in there does. And if you recall back to the video on statistics, we talked a little bit about how we interpret beta 1 and each of these regression coefficients. What we're going to explore in the next video is a little bit more detail on how we interpret beta 1, or any beta for that matter, and how that actually helps us to think about a causal effect of X on Y, or in this case, health insurance on health. Okay, so that's what we're going to be exploring in the next video. We're going to be looking at the interpretation of beta and ultimately what this is looking like when we're building these models. Okay, so I'll see you in the next video. Talk to you then. Thanks. How long was that? No! Fucking A. Testing, working, test.